Hello and welcome to the video for the practice problems. First, I'm just going to show the blank worksheet for anyone who does not have access to the worksheet for some reason. So you can pause the video and copy these down. And then I'm going to show the answer key quickly so you can check your own answers. And if you got everything correct, there's no need to continue the video after you check the answer key. This is a closed circle. This is an open circle. But if you do have any questions, you can stay tuned because after I finish showing you the answer key, I'll go do a walkthrough of the answer key with you. So we're looking for these answers. You may or may not have work. More work, less work is fine. And these are the answers here. This is the work that I did, so you only need the answers. Pause the video if you need to see that longer. And here are the answers for 5 and 6. Again, the amount of work you have is up to you at this point. But this is the only correct answer, and this is the only correct answer. If you have 3 pi over 2 here, that is not correct. All right, now let's go through the answer key. So for the first one, number 1, I would like to actually do that problem. Sometimes I can just kind of point out the different things about the question and you can follow along. But I think for this one, you have to see it in action. So what we're going to want to do is graph cosine using that function anywhere where x is bigger than pi over 2. So the graph paper here has decimals for pi over 2 pi, 3 pi over 2, and 2 pi. The y-axis is not labeled, so I'll just use a scale of 1. I don't see that being a problem with the functions that I have. I don't see any big vertical stretches or major vertical shifts. We have a vertical stretch and a vertical shift, but they're not really large numbers. All right, so for cosine, we want to use cosine where x is bigger than pi over 2. So if you use a pencil, you can just graph cosine and then erase the parts you don't want. No big deal. So for cosine, you're going to start at a y-intercept of 0, 1, because it's that nice even function. And then you're going to, at every quadrant angle, you're going to have a critical value. So if you have a max at 0, 1, you're going to have an x-intercept, which is also a point of inflection at pi over 2, 0. You're going to have a minimum at pi. You're going to have an x-intercept at 3 pi over 2, and back up to a max at 2 pi, because the period is 2 pi. Now you only want to keep this graph where x is greater than pi over 2. So at pi over 2, we're going to put an open circle, and we're going to keep the part to the right. So it's very helpful if you do this in pencil as you're kind of starting so that you can erase the parts you don't want. I personally find that much easier than trying to just graph the part that I want, especially when it comes to trig functions like this, because that barely even looks like cosine anymore. All right, now we want to graph sine with a vertical stretch and a vertical shift. So with our sequence of transformations, we're going to start with sine, and we're going to do the vertical stretch first and then the vertical shift. Okay, so here's the beginning of my sine graph. The vertical shift is going to keep my x-intercepts where they are, but move my maximums up to a height of 2, and move my minimums down to a height of -2, a y value of -2. And I'm not finishing this part of the graph out to the right because I know I'm not going to keep this part. I'm only going to keep this where x is less than or equal to pi over 2. But it kind of helps me to draw a little more of it just to see that shape. So this is sine, and now I want to move it up 1. So you can grab a different color, or you can start erasing some of the graphs that you have underneath. Let's start erasing some. And we're going to move this graph up 1. So this is no longer an x-intercept at 0, 0. It is still a y-intercept, but it moves up to 0, 1. This minimum is going to move up 1 unit. This x-intercept will no longer be an x-intercept. It will still be a point of inflection, but no longer an x-intercept. And when you're done moving all those points up 1, you can connect the dots to get your sine graph. And for some of you, you like to graph the midline or visualize the midline because that helps you see the vertical stretch and the vertical shift. So the midline here would be y equals 1 because the vertical shift is always where the midline is. And then we only want to keep the part of the graph where x is less than or equal to pi over 2. So at pi over 2, I'm going to put a closed circle and only keep the part to the left. So really I'm finished now, but I'm just going to go ahead and trace over this with red pen just to be consistent because that whole entire Now everything that's in red is what I was looking for. So that's how I got the graph that I showed in the answer key. Okay, for number 2. Once again, sometimes I just kind of point out the work I did, but I think you have to see these in action if you do have questions. So without using your notes, where's tangent undefined? Okay, the way I go about this is I think about the graph. So I know my basic tangent graph looks kind of like x cubed, except it has asymptotes. I know the period is pi. And I also know that my first set of asymptotes are at negative pi over 2 and positive pi over 2. So this asymptote is at negative pi over 2. This one's at positive pi over 2. They should be pi apart. So pi further to the right would be 3 pi over 2. And pi further to the right would be 5 pi over 2. Because anytime you're adding pi, you can think of that as 2 pi over 2. Or another way to figure out where all those asymptotes are is to realize that your asymptotes will have an x-intercept halfway in between. So this x-intercept is at 0. Halfway between here, this x-intercept is at pi. My sketch is not very accurate, but that's what I was going for. And then the next x-intercept is at 2 pi. And look at the x-intercepts. They are pi apart because the period of tangent is pi. So by getting this little sketch going, we can figure out where tangent is undefined. It's undefined everywhere there's an asymptote. But we only want to know in between 0 and 2 pi. So we're not interested in that negative pi over 2 over there. But we are interested in pi over 2 and 3 pi over 2. Tangent is also undefined at 5 pi over 2, but that's not within the window that I asked you to look at. Another way to do this would be to use the unit circle, by the way. So if you wanted to, you could think of between 0 and 2 pi and find out everywhere where tangent, whose definition is y over x, is undefined. So at 0, tangent would be 0 over 1. That's 0. That's why there's an x-intercept. At pi over 2, put y over x, tangent would be undefined. That's why there's an asymptote. Here, tangent would be 0, like here on the graph. And at 3 pi over 2, tangent would be undefined. And at 2 pi, y over x is going to give you 0 again. So you can use the unit circle as well. I've just been thinking about the graphs since we just did the graphing video, so that's why I did the graphing method instead. So likewise with cosecant, if I want to think about cosecant, I actually think about its reciprocal sine first, because I know sine much better than I know cosecant. So there's my sine graph. I have x-intercepts at pi and 2 pi, negative pi and negative 2 pi. I'm not interested in the x-intercepts because for cosecant, the x-intercepts are wherever sine has an x-intercept. The vertical asymptotes for cosecant will be wherever sine has an x-intercept, as long as there's no vertical shift. If there's been a vertical shift, we have to think points of inflection instead. But these are points of inflection also. So this would have that U-shaped curve, U-shaped curve. And for this one, the U-shaped curves actually kind of don't matter because we just want to know where this is undefined. So I didn't actually have to go graphing all those U-shaped curves. All I really had to do was find out where sine is 0. And wherever sine is 0, because sine is the reciprocal of cosecant, we have our answers. So what we're looking for, we're only looking this time between negative pi and pi. So negative pi has an asymptote for cosecant, 0, and pi. There are also asymptotes for cosecant at, that says negative pi. There we go. There are also asymptotes for cosecant at negative 2 pi and 2 pi and many, many other places. But within this particular restricted domain, in these particular x values, these are the 3 answers that we're looking for. Okay, for arc cosine, we want to graph it and give the domain and range. So I start with cosine. I don't memorize what arc cosine looks like because I know cosine so well, so I should use that to my advantage. So cosine looks like this. And to make it one-to-one, because right now it failed the horizontal line test, I want to keep this part right here. So I want to keep a restricted domain from 0 to pi. And the range of that covers the entire range of cosine, which is negative 1 to 1. So this point here is 0, 1. This point is pi over 2, 0. And this point is pi negative 1. So when I go to graph the inverse, I'm going to switch the domain and range. So when I go to graph arc cosine, which is also known as cosine inverse, those are interchangeable. The domain is going to go from -1 to 1, and the range is going to go from 0 to pi. So from -1 to 1 for the domain, I really don't need anything below the x-axis because my range goes from 0 to pi. So if this is 1 here, 1.5 might be about there. And then, because pi over 2 is about 1.5, it's 1.57 approximately. And then pi is about 3.14, so that looks pretty good. And instead of 0, 1, I'm going to have a point at 1, 0, because I reverse the ordered pairs when I have inverses. Instead of pi over 2, 0, I have 0 pi over 2. And instead of pi negative 1, I'm going to have -1 pi. And to connect the dots, I reverse the concavity. From left to right, this is concave down, then up. So this graph will be concave up and then down. Let me smooth that out a little bit, make it look a little nicer. All right. So concave up to concave down. And remember, if you turn your paper or tilt your head, this should look like a cosine graph if you were to extend it. So if you were to extend that, it would look like cosine or depending on how you turn it, cosine or a flip of cosine running up and down the y-axis. Okay. And I mentioned that it could look like the flip, because if you do the same idea with inverse sine, it always looks like it's flipped. Okay. So for cosine, this way looks like it's flipped. This one looks correct though. Okay. But that's another way to kind of remember the concavity is if we never restricted the domain. So if I actually found the inverse of the entire thing, so if I took this entire thing and flipped it over the line y equals x, you would have a cosine graph running up and down the y-axis. So that looks correct for the concavity, if that helps. It's easier for me. It's easier for me just to remember that the concavity switches. So if it goes concave down to up, it goes concave up to down. And then for the last two, I think we can head back to the answer key for these, because I went over these in a little more detail in the video. So here we want to find the angle when the ratio for cosine is negative radical 2 over 2. So using what we practiced in the previous video, review 2, we can find the reference angle. Since inverse cosine is involved, we have to stay between 0 and pi. We're not allowed to go past pi. So we're only allowed in quadrants 1 or 2 because inverse cosine is involved. So of those two quadrants, we select quadrant 2 because cosine is negative. And in quadrant 2, only sine and its reciprocal would be positive. So cosine would indeed be negative. The angle in quadrant 2 that has a pi over 4 reference angle is 3 pi over 4. This is the only correct answer. You should be in radians for this, and you should only have one answer. You can't use something that's coterminal because you have to stay between 0 and pi because inverse cosine was involved. If we were actually just trying to solve this equation, we would normally get 3 pi over 4 and 5 pi over 4, because usually we would accept an angle in quadrant 3 because cosine will also be negative in quadrant 3. But we're not allowed to do that here because we're not actually solving this equation. We're evaluating this. We just rewrote it as this equation because it's more familiar and easier for us to work with. And then for this one, we're looking for the angle that gives us sine is -1. So the moment arc sine or inverse sine is involved, these are your restrictions. And that means you can't go past pi over 2 and you can't go past negative pi over 2. So you are not allowed to the left of the y-axis for this. So I knew this was a quadrant angle because I did check 30, 60, and 45. None of those give me sine as 1. 30 would give me 1/2, 60 would give me radical 3 over 2, and 45 would give me radical 2 over 2. If you were thinking 45, I think you were thinking tangent by accident. Sine of 45 would be radical 2 over 2, not 1. So this is indeed a quadrant angle. There are only 3 choices within the restrictions. Down here is where sine is negative, and you can't call that 3 pi over 2. Because if you think about sketching 3 pi over 2, you go right past pi over 2. Pi over 2 is the biggest angle you're allowed to use. So when you go to sketch 3 pi over 2, you'd have to go right past it. So you can't call that terminal side 3 pi over 2. You have to use a different name for it. You have to use an angle that's coterminal that lives within the restrictions. So we call that angle negative pi over 2 instead. All right. Hope that helped. Have a good day.